All right, so welcome back, you guys. We are making major progress in this content material, and we're really chugging away in this semester. So I wanted to start off by talking about the course project. And I'm putting together an announcement, and I will be sending it out right after class today because I got to move some files around. And so you'll get a course announcement later on this evening that'll say course project. I'm attaching several things here. First off is a grading rubric. Let's see if I can open it up. No, I'll just open it up here. The grading rubric it says 2016, but it hasn't changed much. I wanted to show you that this is how I will be grading or scoring your course project. So this is like my little rubric for the oral report and the written presentation. So the oral report will be made during class time the last week, and then the written report is due the following week during finals week. So the oral presentation only needs to be 5 to 10 minutes long. Please don't go over that because there's 14 of you. So the hardest thing I find is trying to keep it that short, but it's good practice because you're going to have to do short presentations and pack a whole lot of stuff in it frequently in your career. And so trying to boil it down to the most important bits is a good thing to practice. So during that presentation, you need to define, and you can use a slideshow if you'd like. Highly suggest it, it's not required, but define your research question and where you got your data, what variables you are using, and it would be helpful to make a table, like table 1, to describe your sample, then describe which method you're using, an MLM, a GEE, which we're learning Thursday this week and continuing on, and GLMM, which is the last kind of topic we're talking about. The software, we've talked about this at the beginning of the class. There's a lot of publications that don't mention their software, so make sure you do for practice. Talk about what worked and what issues you had come up, what didn't work, how you had to adapt. And you should have at least 2 plots in your presentation. One should be your raw data and one should be model-based. So everyone's situation is slightly different, what kind of plots that would be. And then at the end, you'll have questions from your peers. Emmy, like a mini committee, right? So that's your oral presentation. These are just the things, these little bullets to check off. For the written report, I gave you a very wide range of pages. It can be 3 pages, it can be 30. Please don't go over 30, but 3 would be oodles. And by the time you get a table or 2 and a couple plots, I mean, you're guaranteed to pretty much be over 3 pages. So don't worry about the length. We have to practice being brief, but getting all the important details in. But length shouldn't matter. I'm fine if you want to hand in an HTML. I prefer PDF, but Word is fine as well. Work with whatever you need to work with, either to practice your real process or whichever one's easier for you. Any of those formats are fine for me. You're not going to hand in your RMD file, only a knitted PDF or a Word document, one of those 2. The sections there should be these 4 sections in your document. The background should be very, very brief, like a paragraph. Define the research question and the data, describe the sample, what variables you have, and visualization of the raw data. Could be a spaghetti plot. If it's longitudinal. If it's cross-sectional, that might not make any sense. But background, briefer than you would for a regular project. The methods should be the biggest section, and you can put any background you have on the measurements, the actual scales, scores, the variables you have, but focus in on the statistical analysis section. What method did you use? What software did you use? How did you decide on what to include or not include in your model? Did you run likelihood ratio tests? Did you do bottom up or theoretical modeling? What's your best model and how are you going to compare them? So the method says, what's the game plan? The results are what you get when you follow the steps of the analysis. And that should include probably a table, like a tech reg table of your final model, at least one, and some kind of visualization and what the model kind of says. And then the conclusion, again, is very brief. The conclusion can be a paragraph. It needs to focus on what the statistical conclusions are, not so much the implications in your field. You can add all of that if you want practice, but really focusing on the statistical analysis method and the statistical analysis results. And so those are the bullets I'm going to be looking for to check off. Really great if you focus on what you learned about the process of doing this kind of statistical analysis, more so than what it means in your field, since that's what this class is on. There are some due dates that are coming up for the project. About 2 weeks from now, on November 12th, you need to be exchanging a draft of your document to somebody else in the class. You can partner up, you can get a group of you and do a round robin swap. If you need help, I can connect you with someone else, or you guys can do your own Zoom, you can do an email, you can do Canvas, however's going to work for you. It's a little harder where we're not in person, but get your electronic draft to someone else by the 12th. And then they need to be returned by the 19th. So that's before Thanksgiving. That gives some time for you to do a good review of somebody else's. And then when you get yours back, incorporate their comments. So when you're reviewing what is unclear, it's not just what did they do right and wrong, but what did they leave out in the write-up? What things did you expect to see that you didn't see? What parts didn't flow? Was there a chunk missing? Was there a gap from A to B that they need to fill in? Things like that, as well as just general writing and questions about content.
Sarah, for the peer review, we're just getting them the Word doc or whatever, just the write-up.
Just the write-up. If you and the person you're working with or people you're working with want to exchange your R code, that's up to you. But if you just want to exchange a Word document, that's fine too. So the last thing, the reason I haven't sent this out already is because the last thing is some examples. And so I just pulled together some examples, but I didn't save them in the right spot. So here is, I'll attach these so you can peruse them. None of these are perfect, but these are some other ones that I had turned in last semester. So I highly suggest you follow APA guidelines because that's what your field probably uses, and it's good to practice them. And that's part of the reason I had you get the APA guide. So this is Camille Wynn's from last semester. So she has a title page. So the introduction, very brief. Again, basically a paragraph orienting the reader. She has some raw data plots, and that's all. That's her whole introduction. She has, what are the variables? What are the research questions? Kind of getting into it. Then her methods, she talks about who was in the sample, who's in the sample, what did they measure on the people in the samples, and then here she goes in. Linear mixed models were used to analyze the data in the R statistical environment using the LME4 package. And then she talks about the steps. She has a little descriptive table of her independent, dependent variables. That's an option, not required. And then her results section, she has several different models, and she has a summary, like that compare summary, to compare the models to each other. She did a bottom-up approach. And then here's her final model, which is model 3. And then she has a plot for it. And then that's her conclusion. So you can, and then references, of course. You will for sure need to reference R and the LME4 package probably. You don't have to reference every package you used, but the ones that were core. You don't have to do ggplot and dplyr and all of those, but the core ones that did the analysis. She showed lemur test, R, and then LME4. Those are really good for that. You probably need to have those 4 cited. I would say they're the biggies. So there's several other in here that I will attach. I just want to show you, I think it's this one. Open with Adobe, it looks better that way. Okay, so I will show Allison. She went above and beyond. They found a package that formats in APA like a journal article. See, look how fancy they got. You don't have to get that fancy, but they did. But again, they did a little abstract, bonus points for abstract, but the introduction, again, just 2 paragraphs, 1 to 2 paragraphs. Then the methods, a little bit on the participants, the procedures, the measurements, the data, descriptive statistics with a little table and a raw plot. The results, she has them separated by research question and a little discussion with the final plot. And she added a paragraph about the challenges. Everyone's focusing on a little different thing. Some of you guys are going to run into more issues than others. So write about what it was that stuck out. And then again, the references at the end. Okay. So I will send that today with those examples and those dates in the grading rubric. If you have any questions, let me know ASAP so that we can get that cleared up. Does anyone have any quick questions right off the bat about the course project?
I just have one quick question about getting together with people first. It seems like there's maybe 4 weeks or so between that time and the time that the project is due. So I'm just wondering if you have any suggestions about what to do for not having all the data collected and just not being in a state of having things done.
You don't have your data yet, Mike?
Not all of it.
You've got to have a draft to appear by the 12th of November. So you might just have to use the data that you have available at the, this is what I got to go with for now. If that's a big problem for you, let me know. Most people have their data already in hand. It's previously gathered data. So if you have individual concerns like that, definitely email me and we can Zoom quick and figure out how to handle it. You don't want to like put this off till November 11th. I can guarantee you're going to have a big headache. Do you guys need to take a few minutes to talk amongst yourself about, I can open it up and you guys can figure out who you're going to swap with. I'll sit back. You guys go for it.
Anybody want a partner? Open.
I'll be your partner, Joe. I don't have anyone yet. So
Ariel, awesome. Okay.
okay. Oh, sorry. It's Joey, right?
Yeah, I'll chat you.
Okay, thank you.
Have you guys already, some of you talked to each other about this already? Okay. Okay. Well, I'll let you guys, again, if you're having trouble, you don't know anyone in the class, let me know and I will step in. But you'll probably be happier if you work with someone that you choose. All right, so course projects. So I will be gone till the 8th. I am leaving Saturday night and I'll be gone all of next week. So I will not be here, but you guys can work with each other and you can email me. I'll have limited email in the evening, but then I'll be back on the 8th and we can, late on the 8th. So on the 9th, I can be here to help with anything that's coming up. So I would say, get wrangling your data if it's not ready to go, get fitting your models if you haven't started. Generally speaking, in data analysis, you're gonna spend 80% of your time wrangling that darn data. Getting all your data sets together, merging them, checking for missing data, trying to score, which a lot of times we have a lot of items that have to either be averaged or added up, and some have to be reverse coded, and all of those calculations, and sometimes changing from wide to long or long to wide. All of those things take time. So I wouldn't put them off. Once your data is in the right format, I think you'll find that actually modeling it will go faster than you think, but we usually underestimate the data preparation steps. So try not to put that up and let me know, email sarah.schwartz@usu.edu of questions. Okay. So we are up to our eyeballs in logistic and other versions of general linear regression. So on the discussion board, there's some really good things. So I think, let's see if it's done. Oh, yep. The office hours from last night are now processed and they have gone live just in the last 20 minutes, maybe 10 minutes. So the recording from last night's office hours is up. There were a couple of things I wanted to make sure to point out. one thing is if you're taking code off of the encyclopedia, which is a fantastic idea, there is one caveat, one thing that can throw a hitch. In the tech reg package tables that are on the encyclopedia, in some of them I put a percentage symbol on the headline. Let's see, I'll show you. Where's the table? Right here, here's one. Sometimes I'll put odds ratio OR and then in square brackets a 95 percentage sign CI. If there is a percentage sign right in there in what's going to be the header on the table, HTML doesn't care, but LaTeX gets really grouchy. It doesn't like to have a percentage symbol in a table. There's ways to get around it, but it would just probably be a lot easier if you make sure you take out those percentage symbols in the tech reg, knit reg chunks. It will run in our studio, but when you go to knit, it will throw an error code. Couple other things. If you're having some issues, look at here. There's some other, I put some places to look in the encyclopedia if you're having some issues that will give you some direct examples. Yeah, so Carter, so first person to create your own assignment. And so yes, with logistic regression, as well as all regression, sometimes the likelihood ratio test with the ANOVA command will tell you something different as far as being significant and a better fit than the Bayes factor performance package compare performance. And right now, in the past, the gold standard has been the ANOVA likelihood ratio test. It seems to me, like Julianne pointed out, it seems to me that the Bayes factor tends to err on the side of a more simple model, and it's a newer approach. So that's one of those things that you can talk about, that there's pros and cons to a more simple model versus a more complex model. And sometimes our final model, we have two competing models, and we could compare and contrast what's the same or robust or consistent between the two and what is different between the two. And that's part of the story. And again, that's for multi-level models, single level models, continuous outcomes, logistic, Poisson, negative binomial, all of those types of regression models, the same thing can happen. That's another one. Okay, yeah. So another thing that happens a lot of times is you try to run a likelihood ratio test between any kind of regression models. It's more generic. And sometimes you get an error and it says it can't do it. And it might say something like models not fit to a data set of the same size. Likelihood ratio tests can only be done on nested models that are fit to the same data. Those are the requirements. So often we're going to compare one model to a more complex model. So they're nested, but we have this wild caught data thing that sometimes variables are missing. So when we add more variables to the bigger model, more complex model is fit to a reduced data set because it can only be fit to the complete cases. So what you have to do is refit the models. And this is 10.5.1. Let's see if I can find it. You have to refit the model. So here is one. The data set, the first model only had sex in it. The second model had sex, IQ, age, and weight. And it turns out at least one person is missing either IQ or age or weight. Even if it's only one person missing one of those, these models will not be fit to the same data. So the first model is only going to reduce to people that have life satisfaction and sex. But the second model is only going to run on people that have life satisfaction, sex, IQ, age, and weight. So it could be a smaller subset. So the only way to get around this is to take your data set and filter it down to people that are complete on all of the variables in the most complex model. And I'm saving this as a different name. So my original data set was DF depressed, and now I'm going to call it DF depressed model or reduced or complete, give it another name. And then you're going to rerun your models on that new reduced data set. And I do it, I usually keep the same model name, but add redo or refit or CMP for complete, something at the end of it. And then you can do the likelihood ratio test with the ANOVA between those two models. Again, this is something that happens with all kinds of regression models, not just these. Okay. And then the other thing was putting two models into a table when both of them need, you want to exponentiate the coefficients. They both need separate tech, reg, helper, extract functions. Both of them need their separate extract functions. I think those were the main things on the discussion boards. Anyone else have any homework-ish questions to ask about logistic regression? How are you guys feeling about logistic regression?
Sarah,
Oh, sorry.
go ahead, Carter. Sorry.
This is like a small question just about like interpretation. Is it typical when, like in a paper, if you're presenting the results of a logistic regression, to talk about it in terms of like percentage differences, like we've talked about, like, you know, where it's this group is 45% more likely to, you know, have this outcome, or do you kind of keep it in those like those odds ratio estimates, like the decimal, or is it okay to kind of be more vernacular, I guess you would say?
A lot of times, yeah. So the interpretation, do you interpret it in terms of the logits, the log odds, or probabilities? You can do any of those three. The logit is nice because it's linear, but nobody knows what logit means. And log odds are nice because you just exponentiate, and then we can talk about the percentage increase or decrease, but it's in terms of the odds, and that makes it a little harder. So sometimes going to probability is better. And so I really liked how Hoffman, and we're going to go over several of his examples out of chapters, I think 4 and 5, the one on ordinal and Poisson regression, and I think, yeah, ordinal and Poisson and negative binomial today. And we'll see that often when we plot it, we plot in terms of the probabilities, but we interpret the parameters in terms of the odds ratio. It's the most common, but again, it comes down to who your audience is. So if you're speaking to a bunch of physicians, they're used to logistic regression and talking about odds ratios. But if you're talking to someone like that's more like a parent of elementary school kids, you might want to go down to the probability because that might be easier for them to understand. And so although you can interpret the logits and the odds ratios and the probabilities, there's a different level of sophistication that's required to understand any of those three. Ariel, did you have another comment too?
Yeah, mine was kind of an interpretation question as well, because it seemed like it's easier to interpret the odds ratio when it is over 1, because you can just say the odds are 3 times more likely, and when we calculate by hand, we can just like flip that numerator to denominator. But is there a way to make that more easily interpretable in the output? Or
kind of, sometimes. How's that for an answer? So yes, if the odds ratio, the exponentiated beta, the odds ratio comes out to a number that's bigger than 1, it tends to be easier to interpret, at least for me. So I agree with you there. And so if you have a categorical predictor, you can make the opposite category the reference category. And that's essentially flipping the odds ratio. So you're doing, so a lot of times we'll talk about things, risk factors that increase the odds of something. And so the higher risk would be compared to the reference category that has lower risk. If you're doing males to female, depending on the scenario, you might want males to be referenced or female to be referenced, and you can swap those. And I don't think I've shown you that yet. If it's a continuous variable, it's not as easy to flip it. And so usually you just have to deal with an odds ratio less than 1. In those tables.
Okay. Yeah, thank you. That makes a lot of sense. So in our homework, it would have just been like flipping the race from white to non-white as the reference.
Yeah, whichever one's going to be the reference category.
Okay, thank you.
These are really great questions. The interpretation can be a little tricky. Okay. So I think last time we were doing the depression example. Did we do the depression example? Is that one? We didn't, did we? That doesn't sound right. Yeah. Mike, you're shaking your head no. Thanks for keeping me up. Shall we go through the depression example? This is one that's in Hoffman's book. So this is his chapter 3 example that he starts out with. And I grabbed the data set. So it has ID. Every person in the study has an ID. We know their age, and these looks like these are middle-aged, my kind of people in their 30s and 40s. IQ means probably close to 100. I'm seeing lots of 90s. We got low, medium, high, anxiety. We got depression. We've got sleep. Looks like at least high and low. Sex. We got males and females. Life satisfaction, high and low. Weight. Oh, I think we did do this. Did we do this one? Mike, are you? No? Man, okay. We'll start out with this. So here is the main variable that we want to focus on is, are people satisfied with their life? And this was a question they asked yes or no to. And so even though it's yes or no, they're satisfied, we're going to code it as a 0 if they're not and a 1 if they are. So when I make a scatter plot where I have age on the x-axis and life satisfaction on the y-axis, notice our points are either all at 0 or all at 1. And here I've added with geom smooth method equals LM, I've added a regression line. How many points fall on the line? How many points fall close to that line? How good of a summary is that line? Terrible. So this is an example of what the videos were trying to show last time about how a line does not fit very well if we have all 0s and 1s, because the line, and even more if we extrapolate out, the line's going to go beyond 0 and 1. It's not going to stay in our bounds of 0 and 1. So this is where we want to change over to logistic regression. Does this ring a bell now, Mike? No, we still not? Did we do this one? We really did do this one. Did we? All right, so this is like what's on the homework. If we want to say, what's the probability that someone's happy overall? Here I've taken that life satisfaction variable and I've made a table of the values. So in this sample, there's 117 people. About a little over half, 65, say yes. Say, nope, I'm not happy. And 52 say, yes, I'm happy. So what's the probability someone's happy? 55, and probability is always out of the grand total. That's what makes it between 0 and 1. But the odds that someone are happy is the number that are happy versus the number that are not happy. Now this one could be between 0 and 1. It could not be. So if we define it odds of happy, then it's compared to or divided by not happy. In this case, it comes out to be 0.8. And probability can also be returned from odds if we do, or we can get to odds by probability over 1 minus probability, just showing that those are the same. So odds can be yes or no on the outcome, end of statement. Odds ratio is yes or no on the outcome comparing two groups. So to do an odds ratio, we need odds for 2 different groups. So not only do we need like life satisfaction, our outcome variable, we're going to also use sex. I'm sorry if this is offensive, but we're just going to go with male and female to keep things simple because it's in the textbook. So we're going to cross tabulate how many are happy and not happy in the men versus the women. So if we want the probability that a man is happy, we look in our male column and say there's 14 happy out of the total 21 men. So for men, 2/3 are happy. Go men. For the women, only 38 of the 96 women were happy. So women, less than 40% are happy. Who's more happy? Men, because they have a higher probability of being happy. So we're going to let men be our reference category and women be our female, just because we're going to get an odds ratio less than 1 and we can be uncomfortable with it, Ariel. So our reference category male, if we're going to do odds, now when I do, might help with the homework. On the homework, I say, make this calculation and print it out. This is how I had meant for it to be, and that's why I did it here. When you do this top line of code, if that's all you had in your code chunk, nothing would get printed out because it's going to do the math. It's going to like take the calculator. 14 divided by 7 is 2, and it's going to save the number 2 as odds male, but it won't print anything out. So on another line, I put the name odds men so that it will print out or return the value. So the odds of being happy for men is 2. That's 2 to 1. There's 2 happy for every 1 that isn't. For women, the odds of happy is 0.65. Now, odds are only for one group. The odds ratio compares the 2 groups, and you've got to have one group that you're talking about versus a reference category. So for the odds ratio for sex, I'm going to compare female versus male. So I'm going to take the odds of female and divide it by the odds of male. This is the odds ratio when I do my math. It's about 0.32. We always compare odds ratio to the number 1. So we'd say the odds for women, we have to say, we don't say 33% or 32%. We have to say how different is it than 1? It's about what? 67% lower. So we'd say the odds a female is happy is 62%, 67% lower for women compared to men. So that's how we interpret an odds ratio that's less than 1. And it is awkward. And there's 3 different ways to do it. So I'm just showing that yes, all 3 ways come out to be the same thing. So this is a good for if you choose to do my homework for logistic regression, here is a good totally worked out example for how you do like the first part of your homework assignment. Okay. So we're going to go ahead and do a logistic regression, and the part in this code that tells me it's logistic regression is that we're doing family binomial. That means the outcome has 2 levels with a logit link. So that's what makes this GLM function do logistic regression. So we only have one predictor here, it's sex, and then our outcomes, life satisfaction. This is called an unadjusted model because there's nothing else in our model. We'll get an odds ratio for sex, but not controlling for anything else. If we add some other variables to this model, like IQ and age, then the odds ratio for sex would be an adjusted ratio. So I use that same lingo on the homework assignment. So when we spit out the estimates from our model, these will be in terms of probability, odds, odds ratios, or logits. Which one?
Logits?
They're a logit, log odd ratio, which I can see this one's negative, which means females have a lower chance, but that's about all I can get out of that. Doesn't make a lot of sense to me. You can ask for the summary of the model to get a whole bunch more stuff. One thing I want to point out, these deviance residuals. Notice that the smallest of the deviance residuals was a negative 1.4 and the highest is a 1.3. These should be normally distributed, so you would expect to see them going probably more from negative 2 or 3 to positive 2 or 3. So these are a little, not quite the full range we'd expect if they were normally distributed, but we'll leave it at that. So table, we can make a table. Now the table in Hoffman just has the model. Here it is, but it's usually better to do the logit scale and the odds ratio, or if you're going to do one, only the odds ratio, because these logits, which is just the plain model, are a little hard to interpret. So we use my handy dandy TechReg helper function to extract and exponentiate the coefficients. Here we go. So let's practice interpreting it. For sex. Does this number look familiar? Where did we see this number? 0.3, almost 0.33. That's what we got when we just did the by hands odds ratio. If you do logistic regression with one 2-level categorical predictor, it's the same thing as if you just crunch the numbers from the sample. That's why it's called the unadjusted coefficient, or the unadjusted odds ratio. So the odds that a female is happy is about 1/3 the odds that a male is happy. Okay. Can we do anything with these AIC, BIC, log likelihood, deviance? Can we do anything with those numbers? What can we do with them? What good are they? Why do we have them?
Wouldn't we want to compare it to another model?
Those numbers, those goodness of fit measures, AIC, BIC, log likelihood, deviance, are only good for comparing models to nested models to each other. For a single model, they're like of no good. But I want to point out our sample size here is 117. Okay, so we can do this drop one command that looks at it, and if we drop our one variable, it does a likelihood ratio test for our model compared to the model that drops one of the variables, which is significant. Oh, did we have significance up here for sex? Was sex a significant predictor? Here's our Wald test, the p-value for the Wald test. Less than 0.05, it gains it a star. So yes, the sexes are different on happiness, have different odds. Okay. The performance package, if you only give it one model name, it can't compare it to anything else, but it will give you all those summary statistics listed out. There's lots of R-squared like measures. We've talked about how R-squared is not exactly defined for logistic regression. You have to do a pseudo R-squared. There's different versions. McFadden's has been the most popular in the past. McFadden's R-squared here is 0.03, so 3% of the variance is explained by sex. How do you feel about an R-squared of 3? That's kind of tiny. So there is a difference between men and women, but the effect size or the percent of variance is kind of small. There are lots of different R-squared measures. This Tjors is now one of the hot and upcoming, probably more correct, but notice it comes out with 0.04. It's still kind of in the same neighborhood. Again, which one this is a nice function here. It will spit out McFadden's and a couple other ones. Which one you want to report depends on what your discipline is doing. McFadden's is good because it's nice to use something that's been used in the past so that people can use it in meta-analysis. But personally, I would do maybe 2 of them. McFadden's because people are familiar with it, and this Tjors because it's now being shown by simulation to be a better measure. Okay. We can use SJplot to plot predicted, and it will go to the probability scale. I think. Yeah, so this is This is 70% and this is 60%. So who's got the higher estimate? Who's up higher?
The males.
Men. So we can talk about the odds ratios that women have a third the odds as men, but we can also show it in a probability picture. So Carter, this comes up with what you said. How should we interpret it? We would usually exponentiate the betas and talk about odds ratios, but then often make a plot that goes back to the probability scale to visualize it a little easier. Now, somebody said, can we make predictions? And the answer is yes. So there's lots of different ways to predict. EM means is a nice one. So I can say EM means stands for estimated marginal means. So I'm going to stop and talk about the word marginal for a second. So marginal means like averaged over the population. So this class is called multi-level and marginal modeling, because marginal means population average. It's essentially the fixed effects on average. So on average, what's the probability for men and women to be happy? So we can get the probabilities out instead of just having an odds ratio. So these are the values that were in the plot. For men, what's the probability they're happy? The probability is almost 67%. For women, what's the chance that they're happy? 40%, or probability is about 0.4. So probability scales are more comfortable for us to talk about, and we can get those predictions out and we can plot them. And that's a lot of times what we do, even if we interpret the odds ratio first. So here, this is, I said, let's see, what's the difference between the two? This one, I just said, what are the means? So it gave it to us separately for men and women. On this one, I said pairs. I piped on pairs. So it's doing a pairwise test. And if you're comparing two probabilities, it compares them with an odds ratio. So it will give you a p-value for the odds ratio. Now notice what the p-value here is. It's 0.028. Have we seen that before? Let me scroll up. In an unadjusted odds ratio, that p-value, you can think of it as comparing the probabilities in the two groups, men and women. That's what sex is doing. So the interpretation, how we'd interpret this is we would say on average, so this is population average, the marginal effect, on average, 2 out of 3, every 3 males, it should be, are happy, where females have a quarter lower odds. Their odds are 1/4. And this should be the exponentiated betas, right? I need to fix that. Exponentiated betas. This is Hoffman's example. So, oh, I have the new version. I was going to tell you the page number, but that won't line up with your page numbers. Okay. There are influential plots that you can run to look for outliers. Generally, they're not too helpful. Check out these residuals. They're not very helpful because you get basically 2 lines of residuals for each group. It's just not helpful to do residual diagnostics. Okay, so now we're going to do an adjusted model. So if I want to know, my main research question is what is the role of sex? But now I want to control for age, IQ, and weight, because those things might have a difference. A confounding factor is defined as a variable that's related to the main predictor and the outcome. Is age, weight, are those things related to sex, IQ? Maybe, but are they related to life satisfaction? Maybe. So they might, if we don't control for them, because we didn't randomize them, those things are not random, we need to control for them statistically. So statistical control. I'm going to skip down to our table. Here's sex. Let's look at the odds ratio for sex. I think this is the one that was up above. I have to go back and check it. Ooh, anyone else see anything that pops out at them on this table? What's our sample size now? 99. What was our sample size before? Does anyone remember?
117.
It's 117. Why is our sample size 18 fewer people?
Maybe they didn't have like an age or a weight in the data.
There are at least 18 people that are missing at least one of these variables each. So 5 might be missing IQ, and 5 more are missing age, and maybe 8 are missing all 3 or something. So we definitely have missing data. So odds ratio, all of these odds ratio, Ariel, they're all less than 1. Hooray, right? So let's practice. So after controlling for IQ, age, and weight, what is the role of sex on being happy? Now, after sex, it says female. So how would we interpret this number? Anyone want to give it a go?
I'll try. Sorry. So females are 72% less likely to be happy than males when
Okay,
control.
that's really good. And I catch myself doing this wrong all the time. When we can't say likely, we have to say odds. I know, because likely means probability, and I do it wrong all the time. I catch myself. So females are 73% lower odds of being happy.
Okay.
It's awkward. It really is awkward. Okay. Well, after controlling for all of these things, are any of these things, these other control predictors, are any of them significant? We look at this. Well, I didn't put the summary yet. None of these others get a gold star. None of them get a walled star. But if we try to do an ANOVA model to do the likelihood ratio test, comparing their first model with just sex compared to this model with sex and these other things in it, it won't run. And it will give us that error message because the first model had 117 people and the second model only has 99. So the likelihood ratio test will freak out. So this is where we have to take our data set and filter it down to just complete cases on all the variables that are in the most complicated model and refit our models. And here I'm making a table with both of them in there. So the unadjusted odds ratio, these are extracted, so these are odds ratio. So the unadjusted odds ratio is 0.74. The adjusted is 0.74. Did it change that much? It didn't, because none of these things were significant. So when I do my likelihood ratio test, what does this likelihood ratio test tell us?
The simpler model is better.
The simpler model is better, and the simpler model is the one that just had sex. And we could have guessed that because there's none of the 3 covariates we added got walled stars. So I guess it's not surprising.
What is question on that ANOVA test you were just right there, the likelihood?
Mm-hmm.
I mean, it's not saying why is it that, I mean, I don't see either of those models don't have significant better, do they? I mean,
so it always takes the 2 models. This p-value always tells you if the more complicated model is better.
Even if it's not, I mean, doesn't look like a significant p.
It's not. So the more complicated model is not better than our simple model. And our simple model only had one thing in it. I'm not comparing it to a null model here because I can trust the walled stars. Those walled test stars are valid for single level models. So this is single level logistic regression. When we move to multi-level, the walled stars are not totally reliable. So we need to do likelihood ratio tests, even with a null model. Questions on this example?
Yeah, one last question.
Yeah.
On the odds ratio of the let's just look at the multiple IVs of the odd ratio of 0.7388 right there.
Mhm.
If you scroll up to the one you had the table above, the one Ariel was interpreting right there, yeah, that odds ratio is 0.278. And so it seems like the reference is like flipped. Why is it 0.278 there? And then down below it was 0.7.
Yeah, so this is model the fit GLM2. And this one is fit GLM2 redo, but it has 99 in it. Anyone else see why that's not the same? Sex, IQ, age, and weight. Sex, IQ, age, and weight. I see my mistake. I found it. I'm embarrassed. Maybe you guys have done this before. Check out these models. What are in these models? It says GLM, and I have my formula, and I have data equals. What's missing?
The family equals binomial.
It's not doing
Oh.
logistic regression.
Mhm.
It's doing multiple linear regression, not regular Gaussian continuous variable regression, not logistic regression. Okay, so ignore this last table. This last table I'll have to fix. Embarrassing. Don't look. Don't look. Okay.
No, that's really good to know, because I was thinking like somehow the reference flipped because one was like 78 and one was 22. And so it's
That's
good.
a good thinking. The reference, if the reference category flips, it should go from less than 1 to more than 1 though.
Yeah, okay.
So that's how I know it wasn't just a reference category. And it does still say sex female. Yeah. So since I didn't put the family binomial, this is saying the probability for female is 74% higher. That's weird. So let's not do that one. I'll fix that for you. Okay. Did we do the volunteering example in class yesterday or Thursday? Here's another one where the outcome is they asked these participants in the survey if they had volunteered for a religious organization in the past year. So their answers to that question were either no or yes. So if we look at the scatter plot, depending on their education, does there seem to be a relationship between education and volunteering? What would you say? The more education, the more likely to volunteer, or the less likely to volunteer?
Less.
Well, I did a table, and here are the no, they have not. The average education is 13.3 years. And the yes, they volunteered, the average age is 14. And that is a statistically significant difference. So it looks like those that volunteer on average have more education. But that's a two-way relationship. So maybe I want to say controlling for gender and age, is education still related to volunteering? So I am going to, so here's our data set all ready to go. We have volunteering 0 and 1. Volunteering for a religious organization. I've created a yes, no, 0, 1 variable. Their original one had the word no and the word yes. So I created a yes, no, 0, 1 version of the variable. Okay. So here is my model. I've taken female, that's my sex variable, So what's the reference category for female? The reference category must be
Male.
male. I'm using Z of age. So age, there was a range of ages, but to make the intercept more interpretable, I did a Z-score for age. So I took my age variable and I subtracted the average and divided by the standard deviation. I came up with those numbers from my table. On average, the average age is 44.7. Yes, that's like me. And the standard deviation is 16.85. So I use those numbers to make a Z-score out of age as well as education. Often, here's a life tip. If you're putting variables in a model just as control variables, covariates that you really don't, maybe they're not core research question variables, you just want to control for them. If you make them Z-scores, it's a lot easier to interpret. You don't have to, but it can make it easier. So I'm doing Z-scores of age and education, and I've got my female variable here. And I made sure it is logistic regression because I have family binomial link logit. Okay. So here's my table with both the betas and the standard errors and the logit and exponentiated, so their odds ratio. So what's the connection between females and volunteering? Which number on this line do I want to interpret? Megan, I'll call on you.
I think that you're wanting to look at the first one,
Which one? Which number is it?
0.35.
0.35. So what does 0.35 tell us?
This is what we did yesterday.
Yeah, it takes so much practice. Anyone want to help Meg it out?
I would probably look at the second column, the odds ratio column.
Okay, so which number would that be, Joey?
1.4251.
Okay, 1.42. So what would the 1.4 or 3? 1.43, what does that tell us?
Like the odds of a female, odds of it being a female is up 43% up, higher, or something like that.
43% higher, but the female part's not quite right. Someone want to help Joey fix it?
Could you just say that females are about the odds of females volunteering are about 1.5 times higher than males when controlling for age and education?
Yep. So females are 43% higher odds, or about 1.5. It's close to 1.5. They're 43% more likely than males to volunteer after controlling for age and education, because age and education are in the model as well. So we can statistically control for them. Yeah. Sometimes it takes a couple shots to understand this. Now, which things are significant in this model? There's 3 variables: sex, age, and education. Are all 3 of them significant? They're not. Which female is significant? Which covariate is significant?
The education.
Education. So what's the role of education? Now, this is a continuous covariate, not a categorical.
Is it the higher or I know, well, it's 43%.
43%. Oh, same number, 43%. Yeah. So what 43%?
Is it with every increase in like year of education that there's that much increase in the odds that they will volunteer?
Bingo, gold star for Megan. Yes, for every additional year of education, there is an associated increase of 43% in the odds of volunteering. Yeah. All right, so interpretation, yes. The odds of volunteering for male, now I can ask for predictions, But the odds of male volunteers is, that's pretty small odds. The odds of a female, that's small too. But females have 43% higher odds. Okay, so again, we can use the EM means to get those predictions out on the probability scale. So the probability of male volunteers is only 5% in this population, which these are at least 40-year-olds with pretty moderate, education. Who knows where they came from? You have to be careful. Who can you generalize this to? Can I generalize this to you guys? That 5% of you boys volunteer and 8% of you women volunteer. No, because you can only generalize out to the population on which the sample was drawn. And I don't know where this sample came from. Probably not college students, because they were like in their late 30s and 40s. Okay. Logistic regression. Those odds ratios and probabilities can be tricky. Okay. I would like to extend it into ordered logistic. So this is Hoffman's book, chapter 4. Oh, we need a break. Yeah, Julie, definitely. Should have told me I didn't set my... Okay, let's take a 5-minute break. Then we'll come back for the last little bit. Maybe we'll do that. Okay, so this is the depression logistic regression from the encyclopedia and the Hoffman book. So the original data set had sex, and let's go back to the original data set. If you put the name of a data set, $, then you name of the variable, it'll print it out. And we see that this has levels, male and then female. You can ask for it what the levels are. The first one is the reference category. So if I want to, I'm going to take sex and I'm going to I want to reorder it. Now, if you only have 2 levels, you can just reverse them, but this is a more generic version. Oh, wait just a second. Make sure this ran. Oh, that did not work. Made them all female. That didn't work. Okay, so this variable in the original data set, sex had the levels with male coming before female. But I used this factor relevel, and I said I want female after 0. I want the female to be first. And now female is first. It's a good idea to change the name of the variable. To denote what the non-reference category is usually how we do it. Yeah. And so now instead of sex, I can put male. Let me get you a table. Okay. Okay, so here's the original model. The odds ratio for sex was 0.29, but now when I change it to male, instead of being less than 1, it's more than 1. So now we can say males have more than 3.5 times higher odds. So sometimes it's easier to talk about which group has higher odds instead of which one has lower odds. So in this original model, our odds ratio for sex was a number smaller than 1, but when we recode it, so we're looking at male, it's the odds ratio is bigger than 1. Okay, we don't have that much time left. We've got 15 minutes. So these are the options. Understanding logistic regression is my priority. Once you understand odds ratios with logistic regression, it's not as big of a stretch to go into proportional odds extension or multinomial extension. We can do the ordinal. That's what I was planning on doing, but I'll give you guys the vote. Would you rather do the Poisson negative binomial example? Go over that because we haven't done that yet. Okay, that's what I was thinking, is going over the, so this is in Hoffman, this is chapter what? Poisson is chapter 6. Hoffman. Okay. So this is in the encyclopedia, it's, right now it's number 12, right? Nope. Count outcomes, it's number 14. Count outcomes. So we're going to get a little background on this data set, exploratory tiny bit, and this one I have in here, Poisson regression, lovely typos, negative binomial regression, and there's a 0 inflated versions at the end as well. So this is our quick foray into count outcomes. So important thing with count, we went over this a little bit before, is the difference between Poisson and negative binomial, right? When you would do either one. Poisson and negative binomial are both good for when your outcome is a count where it's only whole numbers starting with 0, 1, 2, 3, 4, and on up. So in this example, volunteer is a variable that is how many times someone has volunteered in a certain, the details are in the book, but how many times someone has volunteered, I think within a year. So how many times could someone volunteer in a year? 365 for every day. But in reality, in this sample, the number, most people, 82% almost, never volunteered. So we have a preponderance or an overwhelming amount of zeros. But then some people did once, like almost 10%. And then a few more twice, all the way up to, we had one person that volunteered 9 times. So if we plot it, this is what it looks like. The big deal with Poisson and negative binomial is they're good for outcomes that are not normally distributed at all and are only whole numbers. Yeah, if you look at this histogram, is that a bell curve? Not even close to a bell curve, right, Allison? It's about as far from a bell curve as we can make it. So in general, kind of, if your average is down in the single digits, your Poisson is often a better fit. If your average is in the 30s and 40s and higher, a negative binomial can be a better fit. The good news is you can actually fit both of them and compare them to each other. Yay, we like when we can compare them and we don't have to guess, right? So we want to see if male and female, again with the male and female, I'm sorry, it's kind of redundant. Do men and women volunteer at different rates? Or do they have a different number of times that they volunteer on average over the course of a year? Mike, do you like this example? Yeah. So here I have a cross tabulation. So eyeballing it, what does it look like? Who volunteers more, men or women? Okay, that's a lot of numbers to digest. What would be better than a table? A plot? Now, who volunteers more, do you think?
The females overall.
Females? We have more females in the 0 category.
Oh, I was reading it backwards.
Yeah, the females are blue. Yeah,
So if you add them up, I guess the males then.
I think there are more females in our study. Yeah, there are more females overall in our sample, but we'd have to compare the average, and that's hard to do here. So we could look at the summary. In the females, 34.5 is the average number of volunteering per year. It's a small number because what's the most common number of volunteering times? 0. So on average, the average number of times someone volunteers is 0.3. So only, it's a very small number. Okay, so we can do like before, we can do a single predictor. Now check out, how similar is the syntax? We still have a GLM, we still have the formula, we still have data equals, we just now say family equals Poisson, link equals, not logit, just plain old log. Plain old log. Because this is a log scale, it's logarithmic scale, this slidey down thing, exponential growth or decay, logarithmic. Okay, so I'm going to come down to the table. Now, when we make the table of our parameters here that come out of Poisson regression are on the log scale. So what do we need to do to interpret instead of the log scale? We need to exponentiate. So I'm using our good old TechReg extractor function. Now, in logistic regression, when we exponentiated, we got odds ratios. In a Poisson regression, when you exponentiate, you get the relative ratio or the instantaneous rate ratio. Sometimes it's IRR, sometimes it's just RR, rate ratio. It compares the averages. Averages are a rate. How many times per, we're not saying how many times they volunteer per year. So on average, we don't interpret the beta, we interpret the exponentiated betas. So on average, females volunteer more or less than men. What number are we going to compare it to? 1. So females volunteer how much more? 10%, because it's 1.095, so it rounds up to 1.1. So females have 10% higher rates of volunteering. Now this is an unadjusted ratio because there's nothing else in the model. So of course the next thing to do would be to add some covariates to control for. And here we go. So I labeled it IRR this time. So after adjusting for race, education, and income, can we still say that females volunteer more? What happened to our rate ratio now? Females volunteer higher. Is it still 10% higher? Now it's almost 30% more. So they volunteer 30% more times per year than males after accounting for race, education, and income. 30% more times per year than men. Okay. So odds ratio, with all of these logistic regression and other generalized, there is no straight up R-squared measure. There are pseudo R-squareds. Again, McFadden's has been prevalent in the past. This nice function will give you all of these. Yeah, question.
Okay, so 30% more, 30% more per year. In Hoffman, I think he would have said, what would he use? 1.2 3 times,
Times as much. Yep.
as much.
Those mean the same thing.
Okay.
Yeah. If the
One of them feels additive,
yeah,
but they're both multiplicative, right?
if something is, if we have, what if we had the tax rate at 30%? The tax rate was 30%. Heavens help us, it never gets that high. But if you had a price of an item, how would you find the price if you added 30%?
You take 1.3 times that value.
So if the tax rate is, it's what, about 6% right now in Cache Valley? So to add 6%, you have to times it by 1.06. So percentages are multiplicative, so it's always compared to 1. So you can either say women volunteer 1.3 times as much, or you can say 32% more, and they mean the same thing. Yeah, we're not used to.
Okay, thank you so much for
regular
clarifying that.
regression does not speak this way. This is, you have to think in terms of like coupons and tax rates and things to, it's a different way because it's multiplicative instead of additive. Now notice the Chajor R squared does not work for count outcomes. See, it says NA, can't do it. Cox and Snell and McFadden are the most prevalent, but obviously there's lots of alternatives. Who knows? So you can get residuals out. These residuals don't look very great. I mean, look at this QQ plot. It's really, really tiny, but what do you guys think about this QQ plot? Does that look like a straight line? No. So Poisson regression, often it fits counts, but it has this really strong assumption in the last 5 minutes. It assumes that the average count and the standard deviation of the count are the same number. So if I come back up to our exploratory, let's see, here we go. Right here. Here is volunteering for everyone. What's the average volunteering times per year? 0.33. What's the standard deviation? 0.88. They're not the same number. And it's actually the variance, so we'd have to square that number, but they're not the same. So because of that reason, the Poisson being assuming that there's no over dispersion, then we often violate that, or that usually doesn't fit the data very well most times. So it will say here, the dispersion, so this is out of when I just fit my Poisson model and ask for this summary of it. It gives you a little line down here. It says dispersion parameter for the Poisson family is taken to be the number 1. That means the mean to variance ratio is 1 to 1. And that's a really, really strong assumption. Usually there's more spread than the average. So we saw the average was 0.33, but the spread standard deviation was 0.88. It's usually over dispersed. And so this is too simple of a model. So the negative binomial allows there to be over dispersion. And in Hawkes's book, they talk about an alpha, but because in Stata, it outputs alpha. This is not the p-value alpha. In R, it does more the traditional theta. If you do 1 divided by theta, you get alpha. If you do 1 divided by alpha, you get theta. They're just the reciprocal of each other. So theta is telling us how much over dispersion there is. And so it's not the number 1, which means that Poisson probably doesn't fit as well. So let's look at the syntax really quick to wrap up today. So we cannot use the GLM function to fit a negative binomial because it's not a true generalized linear model. You have to use this special function from the mass package. It's glm.nb. NB stands for negative binomial, but you still give it a formula like the same and give it the data. We still get coefficients. They're still on the log form, so we have to exponentiate. That says Poisson. Yeah, so theta is in R is the 1 over alpha in Stata. Okay. So we exponentiate, where's the exponentiated? See, this is, I did it too quick today. Let's go back to the Poisson. Poisson count. Okay, so parameter estimates, here we go. So we want this to be the negative binomial. Fit the model, parameter estimates. Right, oh, there it is. Okay, so here's the negative binomial. So again, when we exponentiate our betas estimates, these are in terms of, so for males and females, what do we get for the exponentiated beta with the negative binomial? We get the number 1.33. What was it in the Poisson model? Do you remember? It was about the 1.33-ish, wasn't it? It does, in this case, it didn't change that much to do a negative binomial model compared to a Poisson. Julie, do you have a question? Or are we just tired? What do you think about these residuals? They look better than the Poisson? Mike doesn't like them. Allison, do you like those residuals? No, I don't like them either. They still don't look very good. Now we can compare the performance on the Poisson and the negative binomial. And what does it say is better? The negative binomial fits better than the Poisson by doing the compare performance. If I come back to, yeah, let's see, compare the performance right here. So I compare the performance and the negative binomial fits better. Now, I don't know, does your version of Hoffman go into the zip models, the zero inflated? I'm not going to talk about them much because we don't usually do zero inflated multi-level model. But the reason that our residuals look so horrendous in this model is because we have so many zeros, more than the Poisson or the negative binomial distributions would expect. We have an over preponderance of zeros, and even letting there be over dispersion in the model isn't good enough. So I'll just end today as our 1 minute over saying that there are another kind of model. They're sometimes called two-stage models or hurdle models that first asked, is it zero versus something else? And if it's something else, then to do a Poisson or a negative binomial. And those are the zero inflated models. So if you ever come upon a situation where you have a count and you do Poisson or negative binomial and your residuals still look horrendous, then you probably need to look at a zero inflated model. And I'd be happy to help you with that, or that's what you'd need at Google or ask someone about to go to that. But really, for me, the thing I need you to understand out of this whole week is how to interpret logistic regression coefficients so that we can do it in multi-levels starting Thursday. Okay, so that's why the homework assignment just focused on logistic regression, but there are all these other expansions, especially for counts. Okay, so class is officially over now. I will stick around and answer questions. If you guys have questions still on the homework, try to get those up on the discussion board as soon as possible. If we need to have another office hour, let me know as soon as possible, because I'm going to be prepping to leave toward the end of the week. And so I don't want to leave you stumbling around. I want to help before I have to head out. And with your course projects, remember, let me know about course projects if you need anything or have questions.
Thank you.
Thank you.
If random questions come up as we do a course project, Sarah, is it best to like make a appointment with you through the usual stats studio?